For section 3 of chapter 6, we still look at a similar process of what we talked about in section 2, finding probabilities from a normally distributed variable, except now we're looking at a sample mean and using a sample mean to find probabilities. So before we get into that, I first want to talk about what a sampling distribution is, kind of give you a mental picture, and then I'm going to show you this applet to try to visualize what a sampling distribution represents. So if you consider a population of interest, and you take random samples from this population, and for each certain sample size, let's say the sample size is 20 or 40 or 15, you take random samples of 20 repeatedly, and you find the average of those samples, you start to create something called a sampling distribution of sample means. So a sampling distribution of sample means is a distribution using the means computed from all possible random samples of a specific size taken from a population. So if we have this desired population of interest and I want it to take random samples of 20, that means each sample I take comes from 20 different individual scores, and I find the average of it. A sampling distribution is all possible random samples of size 20 from that population, and it creates a distribution of sample means. And so I'm going to illustrate that in a moment using this applet. Now, that kind of changes things up for us as we talk about how we calculate probability, because right now, when we look at normal distributions, we can only use table E to find the probability for that situation. So as the sample size tends to get larger, then the shape of the distribution of sample means for the sampling distribution tends to approach a normal distribution. So there's two cases we have to consider. The first case, if the original population is already normal or considered normal, then the distribution of sample means will automatically be normal regardless of the sample size. If the original variable or the original population, if that distribution is not normal, then the sampling distribution will only tend to be normal or approximately normal when the sample size is large enough. And generally we look at samples of 30 or more. And so what I want to kind of look at or show you is this sampling distribution applet. So here we have a normal distribution, and I'm going to look at samples of size 5 and then samples of size 20. And I'm going to take, well, first I'm going to take 5 more enemy. So what happens, let me clear, I'll redo it. Clear. I'll let that finish and I'll explain what's going on. So clear. So what happens is that in the first one of sample of size 5, the applet is taking 5 random values from the population, and this is the average for those 5. And the second one is doing 20 samples to find an average. So the second distribution that it's creating with the sample of size 20 gives us a far more accurate average of the population than the sample of size 5. And as we keep repeating this process over and over again, and I can take many, many samples at once, and in fact I can do 10,000, we end up seeing two distributions that have a similar shape to the population. Both distributions, sample of size 5 and sample of size 20, are approximately normal. They have the bell shape. In fact, I can fit a normal curve to it. You can see that it closely models a normal distribution. The only difference is the data is far less dispersed than from the original population. So if we kind of compare, the mean of this population is 16 and the median is also 16. If I go down to the distribution of sample of size 5, meaning every single one of these blue kind of rectangles represented the average of 5 values from that population, its mean is still 16 and its median is still 16. But if I compare the standard deviation, this distribution is far less dispersed than the population, which had a standard deviation of 5. This one has a standard deviation of 2.22. When the sample size gets large enough or larger, like this one, sample of size 20, then we see an even smaller spread because we have more accurate data from the population. And so its standard deviation is 1.113. Now, notice both shapes are approximately normal regardless of the sample size because the population was normal. If I were to change this to skewed, and so this is skewed right, and I were to repeat the same process, sample of size 5, sample of size 20, and let's say I just take 10,000 samples at once, this distribution has a little more skewness to it than this distribution does. And so we see that because of the sample size. And in fact, if I change this to samples of size 2 and repeat it, this has even more skewness than samples of size 5. So as we increase the sample size, and once the sample size gets large enough, then the distribution approaches a normal distribution. We can kind of compare that the blue distribution here does not closely match this normal curve. Neither does this one here with the samples of size 20. It's becoming more normal than the distribution before it, and we can even look at the skewness. Now, you don't ever have to find a value for skewness, but the original distribution has a skewness value of 0.83, and then sample of size 2 is 0.56, so it's becoming less skewed, and then sample of size 20 is 0.25. Now, if I change this to samples of size 25, that's the largest the applet goes. I wish it went to 30 or higher, because ideally we would want larger. We would want a distribution with a large sample size, like samples of size 30 or 40 or 50, and then we can kind of really show you. But the higher the sample size goes, the less skewed the distribution tends to be. So that this applet hopefully illustrates for you a sampling distribution. So what we're looking at today in this lecture video is we want to find the probability of a certain average from a sampling distribution. So we think about that we're still dealing with either a sampling distribution that's considered to be normal because it came from a normal population, or we can consider it to be normal because the sample size is large enough. In either case, that still allows us to use table E like we used in section 2 of chapter 6 when we just had a normally distributed distribution and it was talking about an individual. So no longer are we looking at, in this section, the probability of an individual value from a population. We're looking at the probability of an average from a sampling distribution. That's what we like to talk about in this section. Now, so in section 2, you looked at utilizing this formula to transform values into z-scores. However, in section 3, we are looking at transforming a mean and no longer an individual value. So the formula changes a little bit. So when we have a distribution of sample means and we want to use that to find the probability, then to obtain the z-score, we look at this formula here. So x bar minus mu divided by sigma divided by the square root of n. Now, this value here in the denominator is considered the more or less the standard error of the sample mean. So because we do not know the standard deviation of the sampling distribution, then we're estimating it with this information here. So this is still more or less like the standard deviation here in the formula that we talked about in the previous section to calculate the z-score to find probability. But now our distribution is a sampling distribution, and since we're looking at a mean, the standard deviation of that mean, we're estimating it with that information. So let's look at some examples to kind of compare how we did the process with section 6.2 versus how we'll look at the process with section 6.3. And you'll notice that it's more or less very similar in the respect that you still need to find the z-score, and you'll still look at table E to find the probability or the area under the curve for that z-score. The only difference is the formula has changed a little bit. So systolic blood pressure. Assume that the mean systolic blood pressure of normal adults is 120 millimeters of mercury, and the standard deviation is 5.6. Assume the variable is normally distributed. So we're already been told that the variable, which is the systolic blood pressure, is normally distributed. So in that respect, we don't really have to worry about sample size too much, but we'll still talk about that. If an individual, and so here's the difference, if an individual is selected, so if one person is selected, find the probability that the individual's pressure will be between 120 and 121.8 millimeters of mercury. So we look at this, and first, we know that our population mean is 120. That was given to us. We know the standard deviation is 5.6, and we know normally distributed. Check. That normally, the word normally distributed just lets me know that, you know what, I can use table E to find the probability. But before I do that, I need to know what probability I'm looking for. I want the probability that the individual, so X, is in between 120 and 121.8. That means we have to convert to z-scores and then result to table E. So we change this to a z-score. 120 minus 120 divided by 5.6 is 0. And then 121.8 minus 120 divided by 5.6. That'll give us 1.8 divided by 5.6, which is 0.32. So if I were to just draw out the distribution here, right, this is my normal distribution, my standard normal distribution, and I want this little area here. And so to find that area, we know that we need to result to our table. So I need to look at, I know that 0, anything to the left of 0 is 50%, but still, I can go to my table to look, just to confirm that. So 0, 50%, and then I want 0.32. So here's 0.30, and then 2 is 0.6255. And remember, these values represent the area to the left of that z-score. So when I go back, this area of 0.5000 is the area to the left of this number, and then this area of 0.6255 is the area to the left of 0.32, so it includes the brown and the white. But if I want only the brown, then I need to subtract those two numbers. And so the area in between, which is the probability, is 0.1255, which is about a 13% chance. So if an individual is selected at random from this normally distributed population, then the likeliness that that individual's blood pressure would be between 120 and 121.8 millimeters of mercury would be about a 13% chance. So our second example is a little different. Notice now it says in a sample of 30 adults. So instead of an individual, if a sample of 30 adults is selected at random, find the probability that the sample mean will be between 120 and 128.8 millimeters of mercury. So what this means is now, if we think about in our population, if we were able to create a distribution of all possible samples of size 30 from the population, and if we were to select one of those samples of 30 at random, what's the likeliness that the average blood pressure of those 30 adults would be from 120 to 128.8? So the sampling distribution is normally distributed because the original distribution was normally distributed. If the original distribution was not normally distributed, then we would have to consider, well, is our sample size large enough? In this case, the sample size is large enough. It's 30 or more. If it were 15, it still wouldn't matter because it tells us in the problem that the distribution is normally distributed. So when we look at our probability, now the probability statement is very similar, but it's different. The probability that the sample average is between 120 and 121.8. So that just means that we now have to use a different formula to find the z-score, because we don't know the standard deviation of the sampling distribution. So we look at this as an estimator of that. It's the standard error of the sample mean. It's the technical name for it. So the z-score of 120 for this distribution, still 0, and the z-score for 120.8 from the sampling distribution is not going to be 0.32 anymore, and it'll be 1.6. So that this here affects the z-score when we're dividing the standard deviation by, it's making the standard deviation a lot smaller. If I take 5.6, and when we divide those numbers, as we've seen in the applet, that a sampling distribution is a lot less variable than the population. So this is allowing us to reduce the variability in our sampling distribution. So then we still go through and look for the area. So we already know that the area for 0 is 0.005. And when we go back to this table and look at 1.76, so 1.76, it's 1.7, 0, 1, 2, 3, 4, 5, 6, 9, or 0.9068. Let me scroll up, there's about 6. And then we already know that we would need to subtract the area, so we can draw it just to have a visual of this, kind of look at our sampling distribution here. Same shape, normally distributed, shaded in, and then we're expecting a larger area than before, and of course we have a higher probability. So there's a higher chance that if we take a random sample of 30 adults from the sampling distribution, that the average of that random sample will be between 120 and 120.8 versus just taking one individual out of the population. So we have a higher chance here. All right, let's look at another example. Medicare hospital insurance. The average yearly Medicare hospital insurance benefit per person was $4,064. So that's my sample, that's my population mean. And it says if the benefits are normally distributed, so that's, they're already telling us it's normally distributed, so that's good. With a standard deviation of 460, so that is my sigma. Find the probability that the mean benefit, so the average benefit for a random sample of 20 patients, is either less than 3,800 or more than 4,100. So the sample size is not large enough to assume that the sampling distribution is normally distributed. So it's a good thing that the problem states that, because if the problem had not stated that the original distribution was normally distributed, that means the sampling distribution would not also be normally distributed because the sample size is not large enough. But because it states it here, we're good. If it didn't state it here, then this value would need to be 30 or more for us to assume that the sampling distribution is approximately normal, and then thus we could use table E to find the probability. We just have to get the z-score first. So the probability that the sample mean is less than 3,800, so we find the z-score for that. 3,800 minus the 4,064, and then we go to our table E and we find this value in our table. Now, it may be helpful to draw it so we know that we're looking for this area here in the red. That area represents the probability that the sample average, a randomly selected sample of size 20, will be less than 3,800 for the Medicare hospital insurance. So if I go to the table and I look for that z-score, negative 2.57. So negative 2.5 here, 7. So 0.0051. Or 0.51%. 32% chance that will occur. So that's a pretty unlikely event to occur. And then for our second example, we want more than 4,100. So the probability that the sample mean is more than 4,100, still we need to be able to convert that to a z-score. So we utilize the new z-score formula. It still represents the same thing, that now this sample mean of 4,100 is 0.035 standard deviations away from the mean of 4,064. And again, draw our distribution, and we want to try to visualize what kind of area we're looking for. Now we want more than, so that means it's the area to the right. And so hopefully, by now, the practice you've gotten with utilizing table E, that when I look at the table, the number I get will be the area to the left, which is the area in the white space. So if I go to my table and look at 0.35, there's 0.3 and then 5, 6, 3, 6, 8. If I go back, this doesn't look like I've shaded in more than 50% of the distribution. And the number that we got was 0.6368. So that probability, this in red, would have to be less than that number, right? It's 0 is the 50% mark, and I have less than that shaded in. So that hopefully is a kind of like a little red flag to you, like, oh, it says 0.6368. That couldn't be the answer. So I must have to subtract that from 1. And then the likeliness that the average benefit for a sample of size 20 that's more than $4,100 is going to be about a 32% chance. So more or less, it's a very similar process as section 2. We're just utilizing a different formula because of now we're talking about a sampling distribution of sample means versus just an individual, a distribution that represents individual values. So just make sure that you pay it, at least in section 6.3, it's going to be all the same. It's going to be really no different. There'll be some problems like, if I go back here, the one that I did first, where it wants you to kind of review section 6.2, and then it'll have you do one over a sample and kind of compare those and see what do you notice about the two different probabilities. And then there'll be other problems where you are just looking at, like this one, where both parts are for a sample mean.